Okay, time series data. My favourite time series data, just the modelling of data over time. Okay, and all data basically, everything changes over time. We want to look at the trends. We want to look at how things go up and down over time. So with time series data, we're always going to have, down the bottom here, we're always going to have, this scale is going to be some sort of time frame. So here we've got the time in years. We could have the time in days. We could have the time in minutes or seconds. Depending on how quickly we collect the data. Okay, so if we were studying temperature change in science, we might be collecting the data every second or something like that. Okay, so so this variable down here, the explanatory variable, is always time. So we're saying how something changes over time. So in this example here, we've got the birth rate. The birth rate in Australia, average births per female between 1931 and 2002. And this, we can see it with the numbers. It's just a whole lot of numbers just jumbled together. It doesn't really mean anything. But when we plot it as a graph, it tells a story. Okay, so we can see the birth rate, the average births per female, was down pre-World War II. It was down to about 1 birth per female. Okay, and after the war, and this is where we get the term baby boomers from. After the war, there was a boom in the birth rate. Okay, so this is the period of the baby boomers. And that's why there is such a overpopulation of an older age group now, because 70 or so years ago, 70 to 80 years ago, there was a boom. Okay, and then that birth rate dropped off. Very interestingly, this is around the time when contraception became widely available, and we see the birth rate drop off significantly, and it's leveled out. Okay, so it's we've got an upward trend, we've got a downward trend, and then we've got a reasonably flat trend with a slight downward trend. Okay, so that's time series data, and the features we look for is trend. So the upward trend, I said, the downward trend. The other thing is cycles. So cycles are ups and downs that can't really be explained by the particular time of the year. Okay, so I'll come back to cycles, because the next thing we look at is seasonality. Now, seasonality are ups and downs that are explained by the time of the year. Ice cream sales, high in January, low in July. Okay, it has a seasonal. Every January the ice cream sales go up, every July they'd go down. Okay, so we get this upward and downward trend. So that's seasonality. Okay, so we can see here June, it's low in 98. Then if we go to June to 99, it's the next low point. Then if we go to June to 2000, it's the next low point. Okay, the low points have an increasing trend. There is an increasing trend in this data. So this has got trend and seasonality. And we can see from the high points, December 98 is a high. December 99 is a high. And if we were just to move this, we might find that December 2000 is also a high. Okay, so that's seasonal data. It goes up and down with the seasons. Okay, but cyclical data can't be explained by the seasons. Okay, so it went high between 1900. So in then 1907 or so, there was a high. There was another high around 10 years later. Might be 11. So there's definitely a cycle. So there's 11 year cycle or something like that, 11 or 12 year cycle, and every 11 or 12 years this data, which is sunspots on the sun, it goes up and then it goes down, goes up and then it goes down, and it's got this cycle in there which can't be explained by our calendar. Other things we look for: structural change. We'll have a look at that some further down the track. Possible outliers, and just irregular, random fluctuations. Have a look at this. It goes down, then up, 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 down. They're just random fluctuations. We can see here. It's not smooth. There's little ups and downs, and they're just the random fluctuations. Okay. Structural change. It's moving along. It's reasonably flat at that level. Bang! Something happens, and it drops to that level. Electricity use in kilowatt hours. Okay. So January through late summer, first half of the year, high. Something's happened. Maybe they've had solar panels put on their roof, and it's changed the amount of electricity usage. Just something like that. Okay. An outlier. This one here is an outlier. We've got a nice flat-ish trend with just a few random fluctuations, and we've got this one down here, which affects everything. It drags the average down, does everything. So quite often we ignore an outlier. And there's a little bit of information about the random fluctuations which I've been explaining, but you can see them here as well. Just random fluctuations, a little up, a little down, just completely random fluctuations. Okay, so we want to construct a time series plot using CAS, and on page 200 it works you through how to actually go about constructing a time series plot using CAS, and what I expect that you should do. You can't see it all here. You're going to have to open your books up to page 200 and 201, and I want you to work through the example. So get this data, put this data into a spreadsheet. The year's the first one. Okay, so we just remember when we're using the data, we don't worry. This is just here for our information in the top row. This just tells us what year it is, but we're actually going to label years 1, 2, 3, 4, 5. That's what we're going to use in the time series plot. Just year number 1, 2, 3, 4, 5. Okay, and you can see down here, year 1, 2, 3, 4, 5, the birth rate, and we've got it in there. So go and put that into your CAS. Work your way through the example, page 200 and 201 of your book. So pause the video, go and do that, and then come back, and we'll be on the next page. Okay, so the next little bit we're going to look at is just smoothing a time series using moving means, a moving average. Okay, so the coronavirus recently, they're talking about the 10-day moving average. Okay, and it's been moving down, even though there's been random fluctuations. So we had our first day under 100 deaths, then it went up to, well, it was 94, then it went up to 114, then it was back down into the 70s. Okay, so that was a random fluctuation. Now, the 10-day moving average smooths that random fluctuation out. Okay, so we can actually get a better view of what the trend is, and we can be below the average. So, and depending on how many numbers you've got in your average, the smoother it becomes. The more numbers you've got, the smoother it becomes. But also, the more numbers you've got, the more data that you lose. So we can have a look at here. We can have a look at here a 3-day moving average. So 10, 12, and 6 are averaged to get 9.3. And what happens when we have a 3-day moving average? We lose the first data point. So there is no data point for January because we can't do a 3-day moving average because there's no number before it. We need a number before, the current number, and a number after. Similarly, at the end of the month in December, we lose a data point for December. So our 12 data points, when we go to a 3-month moving average here, our 12 data points become 10. Okay, and we can see all we're doing is averaging the 3 points, and we get a smoother line. And so our original data is the red line here, and our 3-month moving mean is the yellow point, and it is smoother. It's still got this big up, still goes down. It's not that smooth. We lost the first point and the last point, but it is a smoother line. It doesn't have the extremes. It doesn't go up quite as high. It doesn't go down quite as low. So it has been smooth. But a 5 moving mean, a 5 month moving mean or 5 month moving average will be smoother, but we do lose 2 points here. Okay, so we need to, for each month, we need to have the 2 months before it and the 2 months after it, so we lose 2 months at the start and we lose 2 at the end, so our 12 months become just 8 data points. Okay, and we can see it, all we're doing, adding up the first 5 numbers, dividing by 5, and the average is 11. Then we add up the next 5. So you see that each time we go down, that first number drops off and everything else moves across, and there's another next numbers added to the end. Okay, and we can see the blue line here. You can see the blue line here is a much smoother line. Okay, a much smoother line. But we've lost those 2 data points at the end, and start and 2 at the end. Okay, so that's a moving average using means. Then we can have a 2 mean. We can have, so notice that they were 3s and 5s, because 3s and 5s are easy. The current data point, there's 2 before, there's 2 after. There's an even number before and after, and it falls on a data point. When we go to an even number, a 4 or a 2 mean smoothing, the problem is when we go to a 2 mean smoothing, the average is halfway in between. Okay, so the average for Monday and Tuesday is halfway between Monday and Tuesday. Then the average for Tuesday and Wednesday is halfway between them. So we have to do a 2-step one, because we have to have this centering as well, because we can't have a data point that's halfway between. So we need to then average these 2 values to make this this one on the Tuesday in the middle. Okay. So I'm just going to go quickly through the 2 mean, just so you're aware of what it is. So example 5, this one, now we're going to look at median smoothing. Okay, so median smoothing takes the median, the middle value. So we're going to construct a 3 median. Let's get our pen here. We're going to construct a 3 median smooth plot of the time series. So what we're going to do is we're going to look at each 3 data points. So we're looking just at these 3 data points. Block out everything else, just these 3. Okay, going this way, the median. So going up and down the 3 points, the median is right here. Now I've got blue. I don't want blue. I want to go red. So our median point is there. Okay, so now we're just looking at these 3, and we're going up and down, and our median point, so 1, 2, 3, our median point, our middle value going up and down for those 3 is there. Then we're just looking at these 3. So here, our middle point, that's our middle point, that's our low one, that's our high one, so our middle point is there again. So then we're looking at these 3 values, and the middle point for these 3 going up and down just vertically. Our middle point is this one, so it's here. And we're looking at these 3. So we're just moving along and looking at each 3. So the middle point here is right on that one. Up, middle, low. Looking at these 3, up, middle, low. So this one's right on there. Look at these 3, up, middle, low. So this next one is here. And look at these 3, up, low, middle, up. So it's right on that point. Low, middle, up. So we're right over here again, same straight line across. And we look at the last 3, we've got low, middle, up. So we're going to be, the middle is here. And we can then, much better than this. So it was a bit rough. We can fit our smooth line though. Okay, probably just use straight lines between them. And if we have a look down here, I think I've got what it should actually look like. And we should. It looks pretty much what I've got. Okay, so that's a 3 median smooth line. And that example was on page 213 if you want to have a look at it. There's an example, before we go on, there's also an example, example 6 on page 214 of a 5 median smooth line. So it's probably worth your while just to go and have a look at that. By all means, pause the video, go and have a look at it now, and then come back and we're going to look at seasonal indices. Okay, so seasonal indices tell us how much something goes up, how much something goes down. So the average is 1. Okay, so the average we're working with is 1. So a seasonal indice of 1 means it is on average. If it's above 1, it's above average. If it's below 1, it's below average. Okay, so a seasonal indice, so when we've got in our season 12 time periods, the seasonal indices would add to 12. If we're doing quarters, it would add to 4. If we're doing days, it would add to 365. Okay, so it tells us a little bit about the seasonal indices. Equals a number of seasons, and that's pretty much what I just said. And so we've got here September 0.85. That would be, I think I'm telling you something, it's on the next page, 15% below average. Okay, February is 20% above average, 1.20. Okay, so that's an introduction to seasonal indices. So let's have a look at what we've got here. A couple of examples. So a deseasonalized figure is the actual figure divided by the seasonal index. Okay, so here we got an example, example 7 is from your textbook. It's on page 218 if you want to have a look in more detail. So the seasonal index, and let's get rid of the red and go back to a better colour. We've got the actual cold drink sales totaled $15,653 for a particular month, I'm imagining. Okay, the seasonal index is 1.33. So if we want the deseasonalized figure, this is the actual figure. If we want to know the deseasonalized figure, so that when we're deseasonalizing, we're flattening out the data, and that's the whole point of it. Deseasonalizing data flattens out the data. So what we're going to do is the deseasonalized figure is going to be the 15,653 divided by 1.33. And this is why it's good to have your scientific calculator with you. Just do a nice quick calculation, and we get to that equals $11,769.17. So this one, it's 33% above average. So we're basically dropping it down that 33%. So we're dropping all the ones that are above, we're dropping them down. So if we might have some seasonal data that looks like that, and what we're doing is we're making it flat. So the high ones we're dropping down, the low ones we're pushing up. If it was low, we'll be dividing by a number less than 1. So that number, we get a bigger answer here. Okay, so that's what we're doing with deseasonalized data. So the other formula, these two formulas are very closely related, of course. This one is just a transposed version of the first one. So the actual figure is then just a deseasonalized figure times the seasonal index. So if we say that their deseasonalized sales were 10,870 and this seasonal index is 0.85, so the actual value will be one of the downs. Okay, so we're actually going to decrease this value. So we're going to go the actual figure equals 10,870 times 0.85, and we get 9,239.50. So we can see what's happening here. this actual figure of 15,653 was up. We deseasonalised and dropped it down. This actual figure of 9,239 was right down, and when it was deseasonalised, it come up, and they come up, and the only thing that's left is a bit of random fluctuation. Okay. So now we're going to look at calculating seasonal indices. So Mickey runs a shop and wishes to determine quarterly seasonal indices based on the year's sales, which are shown opposite. So they're the actual sales. This is actual data. So the seasonal index, and make sure this is in your bound reference. The seasonal index is the value for the season divided by the season average. So to get the quarterly average, we just add them all up and divide by 4, and we get the average is 923. Okay, so what's happening here is that we're going to get the seasonal index for summer. We go 920 divided by 923, and we get 0.997. For autumn, we go 1085. This is higher than the average. 1085 divided by 923, and we get 1.176. These calculations are done down here. For winter's also higher, much higher even than the seasonal average. Okay, so we go 1241 divided by that, and we get 1.345. And spring is really low. So spring divided by that seasonal average, we get 0.483. Okay, so this one is pretty close to average. Summer is pretty close to average. It's 0.3% below. Winter is 17.6%, autumn is 17.6% above. Winter is 34.5% above average. And spring is 51.7%, nearly 52%, 51.7% below average. Okay. Now, if we have more than 1 year's data, what we do is we calculate the seasonal indices for each year. So what we've just done, we would do for year 1. Now for year 2, we'd take that average and we go that divided by the average. Okay, and we get the seasonal indices for year 2. And then we get the seasonal indices for year 3. And then what we would do is we would average all the seasonal indices. So for summer, we'd average that seasonal indices, not these numbers, but the 0.997 and the 1.007 and the 1.098. We'd average them. Okay, so have a look at example 11. Example 11 is on page 221. I want you to go and have a look at example 11 and just work your way through it and see that you understand what's happening. So right now, pause this video right now and just have a look through example 11 on page 221. When you come back, we'll be on the next page. Okay, I've already spoken a little bit about this. So if we're interpreting 1.03, just means 3% above. 1.15, anything that's 1 point is above, so 1.15 is 15% above. 1.30, which sometimes might be just written as 1.3, is 30% above. 0.52 is 48% below. It's below 1, so it's below average. Okay, so that's how we interpret seasonal indices. Not going to spend much time on that. If we had 0.95, that's 5% below. Okay, that's a reasonably straightforward concept. Okay, so the next little bit, we're going to actually fit a trend line and forecast our data. So we're looking at, what are we looking at? We're looking at example 14 here on page 227. So we have, okay, so in this example, we're actually using the deseasonalized data. Okay, so when we actually fit a trend line, we use the deseasonalized data. So in the textbook, as I said, this example is on page 227 of the textbook. In the preceding pages, if you're going through chapter 6, it actually works you through this Mickey's Shop example. Okay, so this is this seasonalized data. This is the flattened data. And you can still see there's random fluctuations still in there, but it's a lot smoother than it would have otherwise been. We can't see the seasonal trend in there. It's been taken out. So we plot the time series data, we plot the deseasonalized data. Then with our calculator, we find the equation of least fit. So here we've got sales equals 838 plus 32.1 times whatever quarter it is. Once again, it doesn't actually name the quarters. So her data is basically quarters from 1999, 2000, etc. But we do the quarter number. So we're going to interpret the slope. So the slope is this one. So the slope means the slope is 32. So over a 3-year period, sales at Mickey's Shop increased by an average rate of 32 sales per quarter. Okay, that's what the 32 means. So 32 is the slope. So every time we go across one, we're going up 32. Across one quarter, up 32. So there's $32 extra sales every quarter. That's the trend. Okay, so that bit is the trend. And the 838 is just where it was right at the start. Okay, so it's a bit below the actual figure, but that's where the trend line would have been at the start. Now, if we want to actually then make a prediction, so if we want to predict for quarter 15, so we're extrapolating here because we're going to quarter 15, it's an extrapolation. So we just go and put 15 into the equation and we get that in quarter 15, so somewhere over here, we're going to get 1319.5. That is a deseasonalized data. So then we have to take into account the seasonality. So the seasonal index for winter, so this is winter, seasonal index for winter, so we have to work out which quarter it is 1.3, so we've got to multiply that by 1.3, and the actual sales then is going to be 1715. So we have to re-seasonalize the data. Okay, call that re-seasonalize. Deseasonalized data, re-seasonalized data, actual prediction. Okay, so just be aware that you have to do that. You have to actually go and get that actual prediction. So at the end of chapter 6, you should be able to have all of these skills. I'm not going to read them for you, you can read yourself, but you should be able to have all of these skills. So today you're going to work on the chapter 6 review. Just pick some questions out of chapter 6, go through the examples, just make yourself really familiar with time series data in chapter 6. I'll be available to help you if you need it, just ask. Otherwise, all the best, and I'll catch you next time.